In this video, I will demonstrate how to do a hypothesis test for paired data. To do this, we'll look at Section 5 of Chapter 6, Exercise 251 is part of your Wiley Plus homework. Do you think your pulse rate is higher when you're taking a quiz than when you're sitting in a lecture? The data in Table 1 shows pulse rates collected from 10 students in a class lecture and then from the same students during a quiz. The data are stored in the file Quiz Pulse 12. So this is an example of paired data or dependent data because we measured the pulse rates on the same students during a quiz and also during a lecture. So because we took the two measurements on the same student, that's what makes this a matched pairs design, or in other words, we have dependent data. And the appropriate way to analyze a matched pairs design is by first calculating the differences within each pair and then using the mean and standard deviation of the differences like we would with a one sample mean procedure. So here's our formula sheet for Chapter 6, and down at the bottom is the matched pairs formulas, but you can see if I look at the formula here, for my test statistic for matched pairs, it's almost identical to the test statistic for one mean. So once we compute the differences, we are essentially just going to treat it as if it is a one mean problem. So back here, I would first find the differences within each pair. So for student 1, I would take 75 minus 73. That gives me 2. 52 minus 53 is -1. 52 minus 47 is 5. Okay, et cetera, et cetera. I would do that for all 10 students. And then I want to find the mean of those differences and the standard deviation of those differences. One common error that a lot of students make is they want to, just like we're subtracting within each pair to get the differences, they sometimes think they can just subtract the means and subtract the standard deviations to get the mean of the differences and the standard deviation of the differences. Now, mathematically, it does actually work out that the mean of the differences is the same as the difference of the means. Kind of sounds like a tongue twister, right? So if I take 68.8, doing this on my calculator, so 68.8 minus 66.1, then I get 2.7. And as we're going to see in a second here, that actually is the mean of the differences. So it works out to subtract the means, but it does not work out to subtract the standard deviations. And you can probably see that here. If I take 12.5 minus 12.8, I would get -0.3, which is not even a valid value for the standard deviation. To find the standard deviation of the differences, we're going to have to use either Excel or StatKey. So to do that, we're going to open up the data set in Excel. So in Wiley Plus, you can click here for the data set. When you do that, then that will bring up the data file list for our textbook. You would scroll down to where it says Quiz Pulse here, and you can download either the CSV or the Excel file. Then you're going to go ahead and open that up in Excel. So here's what it looked like when I opened that up in Excel. It's got the students, their quiz pulse, and their lecture pulse, just like we saw in the table from the problem itself. Now, in order to do the analysis, what we need is the differences. So I'm going to create another column here. I'm going to call it diff, and I'm going to remind myself how I'm taking those differences. So I'm going to take quiz minus lecture. So I'm going to put that in my header just so I remember what I did. And then I'm going to actually calculate that difference. So I want it to take 75 minus 73. So if I hit equals and then I click on that cell B2, hit subtract, and then click on the C2 cell, that'll give me that difference there. And now I want it to do that for all of the students. So if I click on that first cell, now that I have that formula in there, if I bring my cursor down, watch till the cursor changes to just a different type of plus sign. You can kind of see that there. If I double click on that corner, it will just copy that formula all the way down for me. And now I have all the differences. Once I've calculated the differences, that's really the information I need. I can ignore everything else once I've calculated those differences. Now, as we saw in the formula, what we need are the mean and the standard deviation of those differences in order to find out our test statistic and our p-value. So you can copy and paste this data into StatKey, into the descriptive statistics for one quantitative variable, and have StatKey calculate the mean and standard deviation. Since we've already got the data open in Excel, I actually think it's a lot easier just to do it in here while we're here. So I'll show you how to do that. So first I'm going to look at the mean. So the mean is the same thing as the average. In Excel, they just call it the average. So I'm going to type average, and I just want the regular average here. And I want it to find the average of these differences. So I'm going to put that in there. All right, so the mean of all those differences was 2.7. And remember, that is what we saw on the previous slide when we took the difference of the means. So in that way, that's pretty handy that it works out that way. Now we're going to find the standard deviation of the differences. So I'm going to hit equals again, and then I'm going to start typing in standard deviation. Notice there's a lot of options for standard deviation here. I want to choose the one that says for a sample, which is this STDEV.S here, okay? And once you select the correct formula, if you hit tab, it finishes typing out the rest of the formula for you. Okay, now it's got the parentheses there. It wants to find out what do I want to take the standard deviation of, and I want it to take the standard deviation of those differences again, so I'm highlighting those. And then I'm going to put another parentheses on the other end, and I can see that my standard deviation is 9.93367. So if I rounded that to 3 decimals, that would be 9.934. So that's what I'm going to use in my calculations. All right, so back to my problem here. I did already write out my hypotheses here. When we're doing a paired data test, like we are in section 6.5, then our parameter is a mean difference. So in this case, and I'll write it up here, the parameter is mu d. I put the d subscript to remind me that I'm doing a mean difference. So it's the mean difference in pulse rates. So mean difference in pulse rate for a quiz versus a lecture. Okay, if there's no difference in the pulse rate for a quiz and a lecture, then the mean difference would be 0. So no difference is 0. So our null hypothesis is that the mean of the differences, or the mean difference, is equal to 0. And for my alternative, we wanted to know if the pulse rate was higher when we were taking the quiz. And since we did quiz minus lecture, if we got a positive number for that difference, then that would mean that the quiz was higher. So my alternative is that the mean difference is greater than 0, which would indicate that my pulse rate was higher during the quiz. So that's going to be my alternative hypothesis. All right, now I'm ready to go ahead and find the test statistic and the p-value. So here's my formula. This is straight off the formula sheet. And here's the mean of the differences and the standard deviation of the differences that we found using Excel just a couple minutes ago. And the number of differences I have is equal to 10. So when we're looking at sample size, we're looking at the number of pairs in a paired data design. So now I'm going to take these numbers and I'm going to plug them into my formula here. So I have 2.7 divided by 9.934 over the square root of 10. And when I put that into my calculator, I get t is equal to 0.869. And in Wiley Plus, this one tells you to round to 2 decimal places. So if you're doing that, you would get 0.86 for your 2 decimal places. All right, so now I need to find the p-value. And in order to find the p-value, because I'm dealing with a t distribution, then I need to know how many degrees of freedom I have. So as we can see in our formula sheet, t has degrees of freedom equal to the number of differences minus 1. So in this case, that would be 10 minus 1, or 9 degrees of freedom. Now I'm going to go to StatKey to help me find that p-value. In StatKey, I'm going to come down here to theoretical distributions, and I'm going to choose the t. It's going to ask me how many degrees of freedom I have. I just found out that I have 9 degrees of freedom, so I put in 9 there. Once in here, I am going to click on right tail because my alternative hypothesis said greater than. If my alternative hypothesis would have been less than, I would click on left tail. And if it was not equals to, then I could click on to tail. So I've clicked on right tail because my alternative was greater than, like I mentioned. Now I need to put in the value of my test statistic down here. So I'm going to click here, and my test statistic was 0.859 or 0.86. So I put in my test statistic down there. Once I've done that, this little floating box is my p-value. So my p-value is 0.206. All right, so now I've come up with my test statistic, my p-value. The p-value of 0.206 is actually high, especially if you're using an alpha of 0.05. When p is high, then we keep the guy. So in other words, we're going to fail to reject. So we fail to reject the null hypothesis. We do not have sufficient evidence that pulse rates are higher on average when taking a quiz versus sitting in a lecture. So hopefully that helps you out a little bit when you are dealing with these paired data problems.